Today is going to be how to build things with PyMOL in both small molecules and with proteins. Okay, so first of all, there's a nice resource here called Modeling and Editing Structures, and that web page looks a bit like this, and it goes into a few various different things like how to translate and rotate molecules using command line functions, moving one segment in relation to the rest, splitting states and splitting chains, altering secondary structures and things like this. But it's a nice page full of just good general information for any kind of modeling and manipulation of structures. So go and have a look at that. We normally look at proteins and peptides, so I guess the first thing that we should really talk about is how to make a peptide. It's actually remarkably easy to do so. When you're on a blank screen such as this, you can just hold down, as long as you've clicked in the black screen somewhere, you can just hold down the Alt button, and then you can just type the amino acid letter of interest, such as alanine, leucine, proline, threonine, etc. And that just generates a peptide backbone for you. And you can see that when we're in the editing mode, if you remember, we have these little pick spheres here. Now, if the pick sphere is on the is on the C terminus as it is here, then when you have when you're holding down Alt and you're pushing your next amino acid, you can see that you get a C terminal extension. If you click in black space and then click on the N terminus and hold down Alt and click your next amino acid, you'll see that we are extending from the N terminus. And of course, if you click in black space and you don't click anywhere else, and then you continue to type amino acids, we generate a new amino acid chain. Because we're in editing mode, we can then hold Shift, middle click and drag, and we can move those independently, as long as we've unclicked the pick there. Okay, so then you can get these independent peptide chains. And it's very nice and easy, just using the Alt key. Another way of doing it is using the Fab command. So here we can just say Fab and then an amino acid sequence, and that generates the amino acid sequence for us here. So there's our next peptide sequence. Right, and that's just very simply by doing this. And of course, there's another way that we can do it, and that is using this up here in the top right. There's the builder widget, which opens as this little guy, and he can just slot in up here, and we can build chemicals, and we can build proteins, and we can build nucleic acids. So of course we can click on the protein here, say we want a particular residue. It's asking us which terminals we want to extend from here, or we can just create it as a new object if we want as well. And then say done. And again, if we've picked a particular termini, such as that one there, then we can just click residues here and build our sequence. Now, when you're building with the builder, you can also see there's a drop-down menu here where we can have alpha helix, beta sheet, parallel and anti-parallel, and you can see that because it was automatically on the alpha helix, we've started generating a generic alpha helix here with this particular extension of amino acids that we've put here. So that's also a very easy way to create different secondary structures as well. So you've made a couple of peptides, and what the next thing that you really want to do is to stick them together. Here we can do a beta sheet helix motif by moving these guys together. Well, the first thing that we need to do is that when you have overlapping identifiers, so you can see here that if we were to join these together, that the residue numbers would start overlapping with each other, and there's no other additional identifiers to separate the two atomic selections. So what we first need to do before we do any joining of sequences is to use our alter command here on one of our objects. Actually, we'll do this on object 2, and what we need to do is make sure that our residue numbers exceed the residue numbers that we already had. So here we have up to residue 6, so if we add 6 onto object 2 and then refresh our sequence view, you can see that now our residue numbers will not be overlapping, which then means that we can join these together. And in order to join things together, the easiest way to do it is this command called fuse. Now, if you just use fuse with object 1 and object 2, they don't actually fuse together in a particularly sensible way. So what you should almost always do is to pick your N terminus, pick your C terminus, and then you can type fuse. And what that does is it makes a second copy of one of the objects, and then it attaches one of those objects to one of your initial objects. And here you can see that it doesn't really make a very good job of the peptide bond. You can see that we've lost planarity there of the hydrogen, for example, and maybe the geometry of that peptide bond probably isn't very good either. And of course what you can then do is rotate around your psi angle there in order to bring your two pieces of structure together. Now it's a little bit annoying using the fuse command, because it moves this other part of the structure, which means that if you've put them in a kind of bespoke location, that you kind of undo that. Just to show you as well that yes, you can make alpha helices using the builder widget thing here, but you can also just make helices using the Fab command by putting in this secondary structure 1 for helix, secondary structure 2 for antiparallel, secondary structure 3 for parallel. So for example, we could throw all of those guys in and end up with these 3 different structures here. Okay, where we've got our helix there and our two kinds of beta sheets. Here I'm really just going to try and describe that yes, you can do it with peptides, but you can also kind of do it with proteins. So I'm not going to go into a huge amount of detail here, but essentially we're just going to do the exact same thing. Here we'll take in chlorotoxin, clean it all up, and we'll use this command called split chains, and that does what it says on the tin, is that it splits our CTB into each of the individual chains and makes an individual object per chain there. Can be useful. And then we only want to look at 2 of them, so we'll disable some of those guys, orient around what's left, select our C terminus, and remove. Let's just do this part here first. Okay, so selecting our C terminus. Now, of course, if you're going to join your C terminus to an N terminus, you need to remove what's called this OXT atom, and the OXT is normally this guy here, and you can see here it says OXT. So what we need to do is remove that, and then make a selection of our terminal carbon, and we'll call that the C terminus. So now we've got a C term here, and then we can make a selection of our N terminus, and then again we can use the fuse command, and this time instead of having made a pick using the editing mode, what we've done is made C and N term selections using our normal selection criteria, and then this way what we can do is use the fuse term in order to fuse those together. But of course, as I said before, the problem with doing this is that it makes these gross conformational movements of your 2 components, and it doesn't put them together. You can see it hasn't put them together in any kind of rational sense. I think often, as I said before, the actual peptide bond is often kind of geometrically incorrect. But of course you can use the editing mode with control and right click in order to spin around various bonds in order to make it a bit more sensible. And as I said before, whenever you're doing these kind of things, you've got to make sure that you clean up your identifiers that you have for your 2 chains that you've pushed together. Obviously, if you wanted this to be one molecule, really we should change chain E back to chain D and make sure that the numbers here have been incremented to exceed the numbers here, as I kind of described before, and these here are the commands in which you can do that. So I think that's kind of all that I have to say for building the peptides and building and joining proteins together. There is of course a small molecule builder in PyMOL. Now it does work, but I wouldn't suggest that it would be the first place that you should be going in order to build small molecules, because the internal force field of PyMOL maybe isn't really equipped to deal with making proper minimized structures. But if you're doing something very quickly for a presentation or for a picture, then you can go to your little chemical builder up at the top here, and you can choose various different chemical groups. But we can create a new object here of what was going to become a sugar, for example. So we have this guy, and what we want to do is if you want to make any edits to your structure, the first thing that you should do is click on the atom that you want to change, and then you can just use a different elemental selection up top. So we can stick an oxygen here, we can maybe stick a carbon here, and another oxygen, and so on. And you can see that as I build, when I stick on an oxygen, it automatically sticks the pick icon over the next hydrogen, ready to continue any extensions that you might want to make, which is kind of useful. But there we go, very basic, some kind of rather ugly looking sugar there. Once you've made your structure, it has this clean function here. You should be very careful that you don't use the clean function when you've got a very large molecule loaded up, because it will try and minimize the entire molecule, and that will take a long time. But we can just hit that clean, and you can see that it kind of sorts it out a bit. And obviously if you put on things that are a bit more complicated or potentially more ludicrous, then that can kind of help to make things look a bit more sensible. But as I say, the force field isn't particularly great, so it will often leave errors that you might need to fix. The best thing to do, of course, is to use something like ChemDraw and their three-dimensional feature in there, or use something like OpenBabel, which is a command line tool for making small molecules and translating between different file types. So if you do have some ChemDraw structures that for some reason you haven't made a 3D model in ChemDraw, and you're left with something like an SDF file, you can bring those into PyMOL. But again, I wouldn't necessarily say it's a very good idea, because these files aren't very good at translating from the 2D to the 3D, as you can see here. But again, we can use the clean function, and then that can make some kind of three-dimensional representation. But you can see here that these are neither chairs nor boats in these particular sugars here. So what we'd need to do is stick on our sculpting function here, and then by holding Control and left click and dragging, we can start moving some of these atoms around, trying to maybe get back into a more reasonable conformation for these sugar molecules. But again, as I said, there are probably much better ways to generate these molecules than doing this in PyMOL. But if you want to do something very quickly, you can do something very quick and end up with a structure that at least would look fine for a presentation or something like that. Okay, so some structural transformations. Let's have a look at this. So say that you want to move, we've been moving molecules around by hand quite a lot. For example, in the editing mode, you can hold shift and then you can click and drag, and because these are separate objects, as I've used as split chains, we can move these guys independently of one another. But say you want to do something where you want to make more specific movements. I think I haven't introduced this before, but there's a command called turn, and turn, you give an axis and an amount of degrees, and that turns the camera. But if you want to rotate objects independently of one another, then we're going to use the rotate function. So here we can take one of our objects, 2CHBD, and we can rotate that around the x-axis by 90 degrees, and you can see there we are, nice and simple. And of course we can rotate that back to its initial position. You can also rotate using a vector, so you're rotating around a particular vector here by 45 degrees, for example, here, and again, yeah, we can bring that back to its original position there. So you can either rotate on a particular axis or around a particular vector, and then of course you can translate as well, and this is translating in X, Y, Z, a particular thing, a particular object. And you can see that object is now raised up the Z plane towards the camera. Now it's important to know that also a lot of these rotations and translations aren't actually based on the internal coordinates of the system, they're based on the coordinates of the camera. So if I repeat this same command now that I've moved the camera, it will move towards us again. And if I move it over here and repeat the same command, it will move towards us again, right? So, and it's the exact same thing with these rotations as well. If I rotate E and then move the camera and rotate E, now we've kind of lost our anchor back to our initial starting point. So when you're using these, you've got to be careful of how the camera is positioned, but you can also use that to your advantage. For example, when you're using this orient function, you orient around a symmetry axis of the protein, and then you can use that orientation around one particular symmetry axis to then make rotations or translations based upon that symmetry axis, which you might not be able to do if you're using the internal coordinates of the system without doing some advanced maths. Now I said that it all depends on the camera angle, but you can actually turn that off by using the function camera equals 0, and now I do my rotations here and move the camera around and do it again and move the camera. Oh, well, hopefully this is going to work. Yes, so now we're back in our starting position again, despite the fact that the camera is being moved around, because this command here unhooks the rotations and translations from the camera angle and leaves it back into the internal coordinates of for the model. And why would you ever want to do this? Well, maybe, for example, you're interested in making a dimer of a protein of interest. We can orient so that we're looking straight down the highest symmetry axis. We can create a new object, so we've got 2 of them. We can rotate that by 180 degrees, translate it by some amount that is appropriate, and then do some different colorings and change some of the namings of the object, and that way we can end up with a kind of head-to-tail, like a head-to-head dimer here. And then we can just delete the other rubbish we have on the screen using this command. So now we've just left with our dimer, which we extracted here. And then you can use a little sculpting command. So I think we've introduced sculpting before, and you can see here that we've got lots of clashing where we've placed our 2 proteins together. But we can use some little sculpting commands here, where we activate the sculpting protocol. We tell it to iterate over 1,000 cycles of sculpting, and then we deactivate it again. It's pretty simple stuff. So we can throw that in, and you'll see that it will do all the calculations, and then it will generate a unclashed version of that interface for us. And again, this is using the same inbuilt force field that it uses to do the cleaning, but of course it's only looking to minimize clashes in the sculpting. And that way, if you're interested in making some kind of supramolecular assemblies or interactions, that's the way that you can go about doing that. This is just an example of a bit of a less specific example. But here, what we can do is we can just remove one of our subunits here, and then we can show some surfaces and do some colouring in order to have a look at some of the biochemical interfaces that make up the cholera interaction here. For example, we can see quite clearly now that we've got this nice hydrophobic lump here, and that sticks into a little hydrophobic pocket here, and that we've got this kind of chain here of the side of a beta sheet, and you can see that kind of interacts here with the side of this beta sheet. So I thought I'd leave you with one final example, which is maybe you're interested in making a single-chained Lumazine synthase. So Lumazine synthase is one of these example proteins that I've been using throughout the tutorials, where it's a pentamer, and for whatever reason, sometimes it's interesting when you have oligomers to link the chains together and have a single chain version of the oligomer, and therefore you can make specific subunit changes. For example, you could have a pentamer that only has 1 lysine on it or something like this, and therefore you could attach a single fluorophore per pentamer, and you can make some kind of quantitative analysis from that. So maybe you want to design one of these guys that only has a single chain rather than 5 chains put together. So how would you go about doing something like that? Well, this is obviously just a very, very quick and dirty example, but essentially what we want to do is we want to attach the N terminus or the C terminus of one chain onto the N terminus of another chain. And it's not too difficult, and we'll just use some of the commands that I've shown you previously in order to go about doing that. So it's always good to look at the actual sticks, because we need to see the individual atoms here. So what we'll do is we'll make a selection of the N-terminal nitrogen of one of our chains here, and then because we've got a selection using the pick in the editing mode, we can then use the fabricating command here to fabricate an amino acid chain just having glycines and serines, which should be a nice flexible linker, and that can look something like this. Now we can do some pretty funky stuff using the sculpting technique here. There's a command called flag, which you can have free or flag fix. So this just defaults to make sure that all things can freely move when we sculpt, and then we'll use our actual flag command here where we're going to fix everything except for the things that we've selected. So what we'll do is we'll make a selection of our new section here. We'll enter in our command to fix all atoms except for the ones that I've selected, and then we'll turn on auto sculpting. And when auto sculpting is turned on, if we are in the editing mode, what we can do is as soon as we try and move an atom, so to do this it would be holding down Control and then using the left click. We can click and drag while holding Control, and then we have the sculpting feature, which is again this kind of force field that's internal to PyMOL, but it's only having any action on the highlighted sequence that we had here, because here we've fixed all the other atoms to remain stable. So what we can then do is take our peptide chain extension, and we can move that over to the C-terminus of our next residue, of our next oligomer, which is over here. So this is our OXT atom again here. And what we can then, I guess, try and do is align our peptide chain to this in such a way that we can overlap our peptide bond here. Oh, that's not working very well actually. There we go, that's kind of close. I mean, obviously, if you're doing this yourself, you can pay a bit more attention to making this work. And then what we can do is turn off the sculpting, and we're left with, I mean, that is a very choppy orientation there, but never mind. And then what we can do is we can remove our remaining residues that we didn't use. We can select our OXT, which now won't exist because that is no longer going to be the C-terminus, and we can remove that. And then we can reposition our actual guys. Oh, that's going to be a very dodgy peptide bond. And that way you can see that we've just basically dragged a chain over here. This is all just purely for kind of conceptual imagery, I guess. And then what we can do, once we've done these, we can take these two objects that we've made, where we've kind of linked them together, or not quite linked them together, but at least put the atoms into a relatively close position. Make a copy of that to be object 1, and then we can use some commands to create 5 new versions of that copy. So therefore that's 5 new extensions, and then we can align those copies that we had back to the original protein. Then we can make some alterations to their numbering, as I said before, in order to make sure that when we stick them back together that they are different structures with independent identifiers. And then we've got, so basically we've now got 5 models, and each model has got 2 chains, and the second chain has got our extension on it. So actually our first chain is completely unnecessary. So what we can do is take our first chain of each of these models and remove those atoms, and that now leaves us only with the last chain of each of those models, but each of those has this extension. So you can see that we've got now five copies of that, of our extended section here, linking between the N and the C's. So what we could finally do is take each of these guys, extract them as a single object, and because we've changed the nomenclature as well, they're not overlapping, and we can choose atoms independent of one another. And then we can zoom back into our extraordinarily dodgy bond that we'd made here. And because of the way that I've done it, it's basically put the OXT atoms back into the same place. Choose our OXT again, remove that atom, reposition some of our atoms, and then click on the two things that we want to join together and type the word bond. And then we can repeat that process on each of these guys, and we end up with a single chain protein that when we let's just see, when we make into the kind of spectrum view, you can see that this is our now our new N and C termini, with these guys not being bonded, but that then we have a single polypeptide chain which can link through the entire protein. And I think actually that is everything that I wanted to cover. As I said, there's not really a great deal to look at. I mean, most of it really is inside this building widget here, but Fabricate is a great way of making peptides very easily. Fabricate with the secondary structure points on it is very easy, and PyMOL has an inbuilt force field which can kind of help with some of your problems, but most of the time it's best to go to a more dedicated piece of software in order to make small molecules. Does anyone have any questions?